Look at it as a system. What goes into a washing machine? We've got energy, detergent, water and dirty clothes. Pretty simple stuff. Then in the outputs we've got clean clothes, water containing detergent and dirt, one of the largest environmental contaminants from the washing process. And we also produce heat energy. So let's redesign our washing machine. Got a basket of dirty clothes, in they go. What are we going to do with the water? Well, what if we cycled the water continuously in our washing machine? Recleaning it, reusing it, so that we don't rely on any more water input, or maybe a very small amount due to leakage. Then we can do the same with our detergent. We can cycle it. That's already happening in the industrial process. Chemical companies have realised that they want to hold on to their chemicals, so they've worked out ways of scrubbing and recollecting the chemicals from these processes. Then we rely on renewable energy. Now, the washing machine could have a battery in it. This battery could be hooked up to a smart grid, and so it could charge during, say, sunlight hours, and it could sell that energy back to the grid, a percentage of that energy back to the grid when the grid was at the highest price. So that's a possibility, and then it would always keep enough energy for a wash, and it would learn how much energy it needed for a wash. So that battery would in effect become part of the grid, but it would also ensure that the washing machine was using renewable energy. Now, the dirt that comes out could be biological and therefore go to the compost. If our clothes are non-toxic and the process of scrubbing the chemicals results in a non-toxic dirt, then we would see that could go into the compost. And then finally, hey presto, we have clean clothes. Maybe not folded, but certainly dried because we wanted to recover our water, and they're clean. So I just want to go back to the idea of effectiveness and look at water to go into more detail on that idea. The washing machine, average washing machine uses 30 to 45 litres of water, and let's say you do 100 washes a year in a household, you use 3,000 litres. The efficiency model would be to challenge that and go, okay, how do we reduce the water load? Let's use less water. So let's halve it. That's a great goal. And so we save 1,500 litres per household per year. Sounds good. However, what if we increase the amount of water of the average washing machine to 90 litres per wash, but solely, as in the example before? A saving of 1,410 litres per 100 washes. Let's multiply that out across a city of 500,000. This equals a saving of 7 million litres. Now the difference here is that counterintuitively we've increased the amount of material instead of trying to reduce it. And we've probably done the same throughout the whole washing machine, where there once was a pressure to reduce the size of a clip on the door, or to use a cheaper material. We've been able to use something more expensive and maybe even more material to allow that washing machine, the actual physical washing machine, to stay in the economy for longer. So this is the difference between the drive of efficiency in materials and the idea of effective design.